This online lecture is an introduction to how the NMR machine works, its principles, and how to read the data. And here are our key points here. Number one, we're going to see because of its charge and spin, a nucleus can behave like a magnet. We're also going to see number two, that NMR spectroscopy operates by applying a magnetic field to nuclei and then measuring the amount of energy necessary to put various nuclei in what's called resonance. And number three, we're also going to see here that nuclei in different electronic environments, that is either being shielded or de-shielded, require different amounts of energy to bring them into resonance. And we're also going to see number four, an NMR spectrum provides a signal or peak representing the energy necessary to bring each nuclei into resonance. All of these are very profound, so let's make sure we walk through this and get all of them here. And we'll start with our first key point. Consider the hydrogen atom. Remember, what he simply is a proton with one electron circulating around him. What's very key here, though, is that this proton right here has a certain spin, let's say. And because of its spin, it just so happens to give hydrogen atoms a property that makes them behave like magnets. So you could almost think of a hydrogen atom acting as a magnet. Why is this so? This is way beyond organic chemistry. That's a job for physics. We just have to know that hydrogens can behave like magnets. But they're not the only atoms that can behave like magnets. Technically, any one of these atoms right here can behave as magnets. The key features are, one, having an odd number of protons, or you have an odd number of neutrons, or simply you have both. Any atoms with these characteristics will behave like a magnet. Now, let me show you an alternative way to represent a magnet. Instead of drawing pictures like this, you can actually represent a magnet almost like a vector, with the arrow pointing towards the north end of the magnet and the other side on the south end of the magnet. What this simply does is enable us to represent our magnet in different orientations, such as pointing to the upper right-hand corner like you see here, or pointing down like this, or like this, any way we want. In this section, this is how we're going to be representing our magnets. Let's also remind ourselves of how magnets behave. Maybe you've had them or played with them when you were a little kid, and you might remember that when you take one magnet, let's say this blue one, and stick it close to another magnet, it has an effect on that magnet. What would happen is the north ends of these magnets would repel each other, and the north would be attracted to the south end of the magnet. So in response here, the pink magnet would move this way, like this. So what we're seeing here is that magnets can affect the orientation of other magnets. But let's look at this through the eyes of physics here. One way to conceptualize magnets is to think of them as being surrounded by magnetic fields, and these magnetic fields have directions and magnitudes. So for instance, for our blue magnet here, we can say that he's generating a magnetic field this way. And typically, magnetic fields are given the symbol B. So another way to understand the influence of magnetic fields is that if we again move this magnet close to the other pink magnet here, then the result is that this pink magnet orients itself with the magnetic field in this direction. In this section, we're going to be representing magnetic fields as these blue arrows, which from now on, as you can see here, are going to influence the orientation of other magnets. So now let's talk about what happens when we stick these magnets in a machine such as the NMR. Let's say we're putting this in our NMR like this right here. And just think of the NMR as simply containing a chamber where a magnet or a sample could be inserted, and that chamber is being influenced by a big magnet here in red. And let's even do this. Let's represent our magnet as our vector here like this. This is expressing his orientation. And let's say, for instance, we turn on the magnet of the NMR, and when that magnet gets turned on, this is the direction of the magnetic field that he creates. And we're going to call that the applied magnetic field. It's simply the magnetic field applied by the magnet in the NMR. Now remember, what effect would that have on our magnetic here? Well, remember, he will orient himself with the magnetic field like this. And let's pause for some vocab here. If this happens, we are saying that this magnet is in what's called the alpha spin state. And we need to know that this particular state is considered the lower energy state, or more stable state. However, this is not the only possible outcome here. Let's go back to the beginning here. Again, if we turn on our NMR machine and the applied magnetic field runs in this direction, then it's also possible that your magnet could get stuck in this orientation. Notice it's parallel to the magnetic field but pointing in the exact opposite direction. In this section, we're going to call this the beta spin state. And we need to know that this would be the higher energy state. We should also understand that very few magnets would actually do something like this. Most magnets would orient themselves with the magnetic field in the alpha spin state. So now let's apply what we just learned here to an actual H atom. And again, let's represent our H atom as some kind of magnet with this orientation. And let's pretend he's in some particular environment. And let's pretend on the right side of our screen we have another H atom, and this happens to be his magnetic orientation. But let's say his environment is different from the one on the left. For instance, let's say he just so happens to be surrounded by many electrons. Now, if this is the case, let's pretend we stick both of these separately in the NMR machine. And let's focus on the left side first. Again, if we turn on the NMR and the magnetic field runs this way, then we can expect the H atom to orient himself with the magnetic field like this. However, what happens to the nuclei on the right? How does the electrons change things here? Well, first of all, we should know that what's happening is this H atom on the right would have something called diamagnetic shielding, which simply means he's being shielded by these electrons. And shielded from what? Well, in this case, shielded from the effect of the magnetic field applied by the NMR machine. So look at this diagram here. It's almost as if these electrons are shielding it or protecting it from the applied magnetic field. Which means this hydrogen atom on the right here is most likely not going to change his orientation. He'll stay exactly how he is. However, what if we do something like this? Let's say we hook up some kind of light source. And this light source has the ability to produce RF radiation, or radio frequency radiation. Remember, this is a form of electromagnetic radiation, which means this light is carrying energy and delivering its energy to the H atom. What can possibly happen here is that the light energy could give this H atom enough energy to move into the beta spin state like this, which remember is the higher energy position. Let's call this energy E1. So E1 is the amount of energy necessary to bring the left H atom into the beta spin state. Now let's do the same thing to the H atom on the right here. Again, we set up our light source here, we shine radiation at him, and the radiation is going to deliver energy to him. And let's say we give enough radiation energy here to knock him into the beta spin state. Let's call that E2. So E2 is the energy necessary to bring the right-hand H atom into the beta spin state. Now, let's pause for a second here for vocab. What we would say here is that both of these H atoms, now both oriented in the same direction, that is up, we would say that these H atoms or nuclei are in what's called resonance. Resonance meaning same. And think about E1 here, this energy, compared to E2 energy. What would be their relative amounts? Meaning which H atom would require more energy to bring it into resonance? Well, think about it. The H atom on the left has to turn one full 180-degree turn. If you notice, that's a much greater distance of travel than the H atom on the right. He only has to just turn just a little bit to go to the beta state. So that means energy 1 must be a higher value or more than energy 2. Now, what does this all mean? Well, let's see what the NMR would deliver as its data for what we have in front of us here. What it would do is spit out this chart that looks like this, and let's pretend on the x-axis is energy. And if we put each one of these H atoms in the NMR, this is the data that it would report. We would simply see two signals, or sometimes called peaks. Each one of these signals would correspond to the amount of energy necessary to bring a particular H atom or nuclei into resonance. For instance, this one right here would be E1 on the left, and the signal on the right would be E2. So for instance, going back to our diagram, let's say we're representing the left hydrogen as A, then this signal right here is due to that A hydrogen. And if we represent the other H atom as B, this would be the signal right here for him. So think about what we're seeing here. Seeing two peaks in the HNMR data technically means that you have two hydrogen atoms in different electronic environments. And let's pause for some vocab here to describe those environments. If you are an H atom surrounded by a bunch of electrons, you're considered to be in a shielded environment. And that would be hydrogen B here. If you don't have a lot of electrons surrounding you, you're considered to be in a de-shielded environment, like hydrogen A. What we proved before was that if you are in a shielded environment, it takes a lower amount of energy to bring you into resonance, and it takes a higher amount of energy to bring a de-shielded hydrogen into resonance. Now, you might be wondering at this point, hey, this is great, but what does this have to do with organic chemistry? And what is the NR machine actually doing for me here? Well, let's look at an actual organic molecule here. Here we have chloroethane. Let's take a look at the type of environment each of the hydrogens here in chloroethane would be in. For instance, let's focus on these hydrogens right here first. Let's represent them as a magnet with this particular orientation. Remember, this magnet represents the nuclei of the H atom, and that nuclei happens to be surrounded by electrons. Where did these electrons come from? Remember, these are atoms. We got carbon, Cl, we got hydrogen. Each atom has protons and electrons. However, remember the principle here. This chlorine is very electronegative. And remember, that means that he attracts electrons. So he in turn would have an influence on the electrons surrounding that H atom. He would pull the electrons this way. What that would effectively do here is make this hydrogen very de-shielded. He simply has no electrons around him, or very few. Compare this electronic environment to these hydrogens right here on the end methyl. Again, let's say this happens to be their magnetic orientation. And let's say these happen to be the electrons that surround them. If you remember correctly here, electronegativity is a local effect. For instance, as you see in this diagram, the electronegativity would only extend to this green bubble here. So any electrons in that vicinity will be sharply moved to the Cl. But the ones not in that bubble will not have as much of a pulling effect. So in other words, the further you are from an electronegative atom, the less the effect of electronegativity. So, going back to our example here, since the three methyl hydrogens are further away from the Cl, we expect less of an electronegative pull on them, which means they will remain around those H atoms, and therefore make them more shielded. So, let's do this. Let's pretend we take our molecule and stick him in the NMR machine. What we saw, remember, is that if you are a hydrogen that is more shielded, it takes lower energy to bring you into resonance. And again, if you're a more de-shielded H atom, then it takes a higher amount of energy to bring you into resonance. So, what would the HNMR spit out as its data for this sample molecule? Well, let's see here. Let's label our hydrogens first. Remember, let's call this guy the A hydrogen, and we'll call these three hydrogens the B-type hydrogens. Putting this sample molecule in the HNMR would give us a spectrum that looks like this. We can expect to see two signals in it. Remember, one for the A-type hydrogens and one signal for the B-type hydrogens. And those two signals again will correspond to the amount of energy necessary to bring these hydrogens into resonance. Now, at this point, you might be thinking, okay, that's great. That's the connection of this to organic chemistry. But still, what does this do for me? Well, I'll get to that in a second, but let's pause for some vocab here. If you get a good look at this spectrum right here, here's what I want you to know. If you're more de-shielded, and again, which means it takes a higher energy to bring you into resonance, and if you're more shielded, let's say, which requires a lower energy to bring you into resonance, the de-shielded peak, what we want to know, would be more downfield. Notice here in your chart, your 0 is on the right-hand side. So a downfield peak is more away from the 0 mark, whereas any peaks that are closer to 0 would be considered upfield peaks. I'm going to be using these terms a lot when we're interpreting NMR spectra. So now, finally here, what does this NMR machine do for us? Well, let's just say you happen to have a sample. In this beaker is some organic substance. And let's say we take this substance right here and we run it through the mass spec. We learned how this machine worked in a previous online lecture, and remember, he had the ability to deliver not only the molecular weight of a compound, but also the possible molecular formula. And let's just say the mass spec happens to say that our sample is C3H7Cl. Let's say we also run it in the IR spec machine, and the IR spec tells us that we see a lot of CH vibrations. Of course, because there's a lot of CH bonds in our molecule. Remember, we also learned how this machine works in a previous online lecture. And notice, if we did a calculation on the degree of unsaturation of our sample, the degree of unsaturation is 0. We talked about how to do this also in another online lecture. And remember, what this 0 means is that our molecule has no double bonds, no triple bonds, or no rings. Now, think about what structures might fit the data at this point. Your molecule could possibly be 1-chloropropane. Notice this molecule does have 3 carbons, 7 hydrogens, and 1 Cl. However, your molecule can also possibly be 2-chloropropane. And if you thought a little bit more about this, you'd realize there's no other possibility. There's no other organic molecule that would have this molecular formula and not be either 1-chloropropane or 2-chloropropane. So at this point, we don't know if it's one or the other. Here is where the NMR is going to help us. Notice, let's place our molecules side by side here. And let's think about the electronic environments of each of the hydrogens in each molecule. So let's start with 1-chloropropane first. Remember, he has this Cl right here, which means these hydrogens right here, let's call them the A hydrogens. Since they're the closest to the electronegative Cl, they would be the most de-shielded. Whereas the hydrogens way on the other end over here, these guys, let's call them B, these would be the most shielded because they're the furthest away from Cl. And these hydrogens right here in the middle, we'll call them the C hydrogens, they'd be, let's say, middle of the road. Not as de-shielded as A, and not as shielded as B. Somewhere in the middle. Which means technically, for this molecule, you have 3 hydrogens and 3 different electronic environments. Which again means if we run this through the NMR and look at the data, we should expect to see 3 signals in the HNMR. Again, 1 signal each for bringing each one of these hydrogens, A, B, and C, into resonance. And why not? Let's label him. Remember, this guy would be our A hydrogen peak, the most de-shielded. This right here would be the B peak, the most shielded. And then remember, C right here would be in the middle of them. So that's what we would get out of the HNMR for that molecule. Now let's do the same type of analysis on 2-chloropropane. Again, we focus on his Cl right here being very electronegative. And let's call this hydrogen right here the A-type hydrogen. Notice, out of all the hydrogens in this molecule, he's the closest to Cl. So he should be the most de-shielded hydrogen. Now, what about the hydrogens on the left here? Let's call them the B-type hydrogens. Notice, whatever they are, they're definitely going to be less de-shielded, simply because they're further away from the Cl than the A hydrogen is. But what about these hydrogens over here? Notice they are an equal distance to the Cl as the B-type hydrogens. So that means these hydrogens are roughly in the same electronic environment. The amount of energy to bring them into resonance would be the same, which means we can also call them therefore B-type hydrogens. They are literally equivalent. So what does that mean here? Again, what would the NMR spit out as its data? Since there are technically two types of hydrogens in this molecule, A and B, we should expect to only see two signals in his HNMR spectra. This would be the signal for the A-type hydrogen, and this would be the signal for the B-type hydrogens. Again, the reason why we're only seeing two signals here is that all the B hydrogens, since they have the same amount of energy to bring them into resonance, all of them would peak on top of each other. They would simply overlap in the data. So that's why we would only see two peaks in his spectrum. So notice it's the HNMR that helps us distinguish these two structures, which means if we throw our unknown sample into the HNMR and we see three signals, we know the molecule has to be 1-chloropropane. If we happen to see two signals, we know the molecule therefore must be 2-chloropropane. So notice, in summary here, by using all of our available machines here, and that is the mass spec, the IR, and the NMR, we can unequivocally determine what our sample molecule is. And take note here, notice it's the combination of more than one machine that's helping us determine the identity of an unknown sample. Each machine plays a very important role. So let's pull it all together here. What have we learned? All right, here's our key points, right? Remember, 1, because of its charge and spin, a nucleus can behave like a magnet. That's very central. We saw that. Number 2, NMR spectroscopy operates by applying a magnetic field to a nuclei and then measuring the amount of energy necessary to put various nuclei in resonance, right? That's key. That's the whole chapter right there, the essence of it. That's what we're leaning on. This is the science behind the concept of how this machine works. Let's look at number 3 here. 3 says nuclei in different electronic environments, in that case shielded or de-shielded, require different amounts of energy to bring them into resonance. Another very important key point. And 4 here, an NMR spectrum provides a signal or peak representing the energy necessary to bring each nuclei into resonance. And this, we're going to see, helps us determine structure.